Good evening, everyone. I am Shivani Dhok and I welcome you all for the week 6 tutorial for the course of Digital Signal Processing and Applications. So like every week, this week's tutorial will also be divided into two parts. The first part will be recap of week 6 content and followed by the questions which are related to the week 6 content. So let's start with the overview or rather recap of week 6 content. So in this week, we started with linear constant coefficient difference equation, which comes from the rational Z transform of a system. That is, if I have a Z transform of a system, or rather a system with a valid Z transform in a rational form, then that system can be represented using this linear constant coefficient difference equation. Okay. After that, we saw that this thing LCCDE or linear constant coefficient difference equation can be realized very well. So basically, if rational systems are having this kind of structure, then we can realize the systems which have rational Z transforms or which are rational. After that, we looked at how to solve the linear constant coefficient difference equation for a finite range of time. Then we also saw the causality and stability with respect to ROC perspective. So we saw that So we saw that if my z equal to infinity is included in my ROC, then the system is causal. And if R equal to 1, that is unit circle, is included in my region of convergence, then the system is stable. After that, we looked at ideal filters. In this ideal filters, we looked at ideal low pass, ideal high pass, ideal band pass, and ideal band stop filter, and we saw that these ideal filters are neither causal nor stable, nor they can be represented, or rather they can be realized because their Z transform is not in this particular rational form. So this was all that was covered in this week 6. So if there are any questions, I'll stop. Otherwise, I'll go on and solve the questions which I had planned to cover today. Okay, if there are no questions, then let me move on with the questions that I have planned to cover today. So the first question here is, if xz is Z transform of a signal xn, then what is the Z transform of the signal yn, which is given by n square xn? Okay. So the things that are given to us are this x of n, this x of n has a Z transform as capital X of z. So we need to find the Z transform of y of n. Let's say this is y of z, and we don't know what this is. And we know that this y of n is n square xn. Okay. Now recall differentiation property. What it says, if x of n has Z transform as x of z, then n times x of n will have Z transform as minus z d dz x of z. Okay. So now this y of n, which is equal to n square xn, can write this as n into n times xn, and we know that this y of z will be, or rather this n times x of n will have a z transform of minus z d dz x of z. So this n square x of n, rather n into this quantity, will be equal to minus n times z transform of this quantity, that is minus z times, or rather minus d dz, sorry, minus z into d dz of the z transform of this quantity here, which is minus z d dz x of z. So now we can apply the chain rule. So this quantity here is our y of z. So therefore this y of z is equal to z, inside the bracket it will be z into d2 by dz square xz plus d dz xz. So this comes out to be z square into d2 by dz square x of z plus z into d dz xz. So this is my y of z, where my y of n is. So this quantity here was my y of n. So therefore this is z transform of this particular signal, which is n square into x of n. Is it clear? Any questions?
Okay, madam.
Yeah. Okay, so if there are no questions, then let me move on to the second question. So this is the second question that we are having here. So what does it say? For all k greater than 0, we need to find z transform of xn, which is equal to sine kn un. Okay, so we have x of n is equal to sine of kn into un. Now this I can also write as this sign here, I can write as e power j kn minus e power minus j kn upon 2j into un. So this we know. And now we need to find x of z, which by definition is summation n running from minus infinity to infinity xn z to the power minus n. Now I can substitute xn as this quantity here. So what we have is summation n running from minus infinity to infinity e power j kn minus e power minus j kn upon 2j un into z to the power minus n. Now since this quantity is having a unit step here, I can just change the limits from 0 to infinity and drop this u of n. So what I have is summation n running from 0 to infinity e power j kn into z to the power minus n plus summation n running from 0 to infinity e power minus j kn z to the power minus n. Okay, so this I can also write as summation n running from 0 to infinity
Madam,
e,
you are missing 1 by 2j.
oh yeah, sorry, thank you. Yeah, this 1 by 2j will be there with both the terms. So I can write this as 1 by 2j summation n running from 0 to infinity e power j k into z power minus 1 to the power n plus summation n running from 0 to infinity e power minus j k z to the power minus 1 to the power n So this quantity here is infinite geometric progression. So this is an infinite geometric progression with first term as 1 and common ratio as e power j k z to the power minus 1, and this will converge if magnitude of r, which is equal to magnitude of z inverse, is less than 1 or magnitude of z is greater than 1. In similar way, this quantity here is also an IGP or infinite geometric progression with first term as 1, common ratio as e power minus jk into z inverse, and this will also converge if magnitude of r is less than 1, and this magnitude of r here is again magnitude of z inverse, which is less than 1, or we can say magnitude of z is greater than 1. Okay, so both of these summations will converge if I have a magnitude of z greater than 1. So this clearly is giving us our region of convergence. So this is the region where my z transform shall converge. Okay. So now if this is an infinite geometric progression, I can write this thing as 1 upon 1 minus e power jk into z inverse plus 1 upon, sorry, this won't be plus, sorry, yeah, minus 1 upon 1 minus e power minus jk into z inverse, and this will converge for magnitude of z greater than 1. So this I can write as 1 upon 2j inside the bracket 1 minus e power minus jk z inverse minus 1 plus e power jk into z inverse upon 1 minus e power jk plus e power minus jk z inverse plus z to the power minus 2. So these terms get cancelled, and what we have is 1 upon 2j inside the bracket e power jk minus e power minus jk z inverse divided by 1 minus e power jk plus e power minus jk z inverse plus z to the power minus 2. So if I consider this term here, so this thing here is simply sine k, and this term here, this term, if I multiply and divide by 2, so I'll have 2 times cos k. So this term here is cos of k but multiplied by a factor of 2. So therefore what we have is, we have this as z inverse into sine k divided by 1 minus 2z inverse cos of k plus z to the power minus 2, and region of convergence is magnitude of z greater than 1. So this is my x of z, or this is z transform of our given signal, which is sine k, sine nk u of k. Is this clear? Any questions?
No question, madam.
Okay. If there are no questions, then let me move on for the third question. So this question says that given an input to a rational system, xn equal to delta n plus delta n minus 1, the observed output was yn equal to un minus 4. Determine the system function. Okay, so now what do we have? We have this x of n as delta n plus delta n minus 1, and y of n is equal to u of n minus u of n minus 4. Now I can also write this y of n as summation n equal to 0 to 3 delta n minus, sorry, not n, k minus k. So why is it so? So if I look at u of n, so my u of n will be like this. This is my u of n, and this is 0, 1, 2, 3, 4, and my u of n minus 4, this will be 0 here, 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 and will be 1 here, 1 after that, and everywhere 1. So u of n minus u of n minus 4 will be 1 at 0, 1 at 1, 1 at 2, 1 at 3, and after that from 4 onwards both of these signals have same value, so it will be 0 everywhere afterwards. So this thing here is delta n, this thing here is an impulse shifted by a 1, this thing here is delta n minus 2, and this thing here is delta n minus 3. Okay, so this quantity un minus 4, I can write it in this form. So purposely I am doing this because my input is also in this form and my output is also in this form. Okay, so now I can write this. Okay, so now I have my input and my output. So now what we need to do is we need to determine what my h of z is. And we know that this h of z is given by y of z upon x of z. Okay, so now let us find out what is x of z and y of z. So my x of n was equal to delta n plus delta n minus 1. So my x of z will be equal to, okay, so to understand this, what we will do is, so we will generalize or will consider delta n minus n naught, and we'll try to find out what is the z transform of this quantity. So if we do that, then this quantity here will be summation n running from minus infinity to infinity delta n minus n naught into z to the power minus n. So this I can write as summation n running from minus infinity to infinity delta n minus n naught z to the power minus n naught, and this quantity here, the summation, is equal to 1. So what I'm left with is simply minus z times n naught. Okay, so what we know is delta n minus n naught will have a z transform at z to the power minus n naught. Okay, so if my x of n is delta n minus delta n, delta n plus delta n minus 1, so my x of z will be equal to, so here if I compare it with delta n minus n naught, my n naught value is 0. So if I substitute n naught equal to 0 in this quantity, then I'll get 1. And similarly here my n naught is 1. So So I'll get plus z to the power minus 1. So this is my x of z. Now similarly, my y of n is summation n running from 0 to 3 delta n minus k, sorry. So therefore this y of z will be equal to, due to linearity, k running from 0 to 3, and delta n minus k will have z to the power minus k. So this I can write as 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3. So this is my y of z. So now what is left is we just need to find out the system function. So therefore system function is h of z is equal to y of z upon x of z, and my y of z is 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3, and my x of z is 1 plus z inverse. So this is my system function or my h of z. This is the final answer that we are having. Any questions? Okay.
Okay, madam.
Okay. If there are no questions, then let's go ahead for the fourth question. So this is the fourth question. What it says is, so it has two subparts. So let's start with the first subpart that we are having here. So the first subpart says, what are the components required for implementing a rational system or a linear constant coefficient difference equation, that is LCCDE, in hardware or software? And the four options given to us are: one sample delay buffer, second option is constant multiplier, third option is two input adders, and fourth option is a constant adder. So if we remember, the difference equation is generally of the form of summation k running from 0 to some m some ck into y of n minus k, which is equal to summation k equal to 0 to n vk into x of n minus k. So here if we observe, what we did is this particular multiplication, this ck into this quantity, this multiplication was carried out by a constant multiplication. This quantity is a constant, so we need a constant multiplier. So yes, this we require. Another thing is, in order to make this shift by k, what we do is we cascade multiple single delay, one sample delay buffer. So therefore this option is also required, that is we also need one sample delay buffer, and we have a summation outside. So instead of having multiple inputs to one adder, what we consider is we consider just a two input adder. That's why this option is also required, that is we require two input adders. But what about this constant adder? Do we require this constant adder in this? For example, what does this constant adder mean? So let's say I have this xn and let's say there is an adder here and I'm adding a constant here, let's say some c. This is y of n. So this y of n is x of n plus c. So do we require this kind of structure? this adder, this is a constant adder. Do we require it? We are trying to implement a rational LCCDE system, and this rational system, we saw that we are using it for an LTI system, that is linear and time invariant system. So if I'm having a linear and time invariant system, and that is in rational form, but if I introduce a constant adder, my input output relationship becomes something like this. And the point you have a constant something like this, you lose on to your additivity or even homogeneity. So since we are having this constant C here, we can't say that our system is a linear system, and that's why we don't require this constant adder. So this we don't need. Okay. So now what we need to do is, using these three blocks which we said that we need to implement this system function, which is h of z. So we have h of z, which is equal to y of z upon xz as 1 minus 4z inverse upon 1 minus 5z inverse plus 6z in z to the power minus 2. So this we can write as y of z multiplied by 1 minus 5z inverse plus 6z to the power minus 2, which is equal to xz multiplied by 1 minus 4z inverse. So what we have is this y of z minus 5z inverse into y of z plus 6z to the power minus 2 into y of z, which is equal to x of z minus 4z inverse into x of z. Now let us take inverse z transform. So what we have is y of n minus 5 times y of n minus 1 plus 6 times y of n minus 2, which is equal to x of n minus 4 times x of n minus 1. Okay. So what do we have? We have y of n is equal to x of n minus 4 times x of n minus 1 plus 5 times y of n minus 1 minus 6 times y of n minus 2. And now we need to realize this system using the three components which we have just discussed. Okay. So now for realizing that system, what do we need? We have this input xn and we have the output which is y of n. Okay, and everything what is happening is between these two quantities. So now this x of n we are having as it is, and that thing gets added with this quantity here, which is minus 4 times x of n minus 1. So now what we need to do is we need to delay this x of n by 1 unit and then multiply it by minus 4, and then it should get added to this quantity here. So here what we are having, so here we are having x of n minus 4 times x of n minus 1. Okay, this is what we are having here, this thing. Okay, but this thing also gets added with the term which is red in color, right? So for that, what it says is, what we will do is, we'll take this y of n, delay it by 1 unit. So this will give me y of n minus 1, and then again pass it through a delay of 1 unit. So this will give me y of n minus 2, and this thing here, what we do is, this y of n minus 2 gets multiplied by a factor of minus 6. In similar way, this y of n minus 1 gets multiplied by a factor of 5, and these two will get added like this. So here what we are having 5 times y of n minus 1 minus 6 times y of n minus 2, and all, so this quantity plus this quantity when added will give me my y of n. So what we need to do is, we need to sum up this thing and this thing to get y of n. Any questions? We'll spend a lot of classes towards the end of this course in understanding the ways to realize this system. So this particular question I just took just to show that how these three components are used. How these three components are used in order to realize a rational function. Any questions?
Okay, madam.
Okay. Okay. Let's move on to the next question then. Okay. So what does it say? Consider the LCCDE which is given here, which is y of n is equal y of n minus 0.7 y of n minus 1 plus 0.1 y of n minus 2, which is equal to 2 times x of n minus x of n minus 2. And what we need to do is, we need to find an approximate expression for the output yn, where my input is x of n equal to 4 to the power n un, and what we are given is this y of n is equal to 0 for all n less than 0. This is my input and this is my LCCD. Okay, so what all things are given to us? We have my linear coefficient difference equation, linear constant coefficient difference equation. So that is y of n minus 0.7 y of n minus 1 plus 0.1 y of n minus 2, which is equal to 2 times x of n minus x of n minus 2. Okay, and we have x of n is equal to 4 to the power n u of n, and we need to find this quantity here, which is approximate equation of y of n. So what we need to do is, we need to find y of n, what it is, and the thing that we know about y of n is this: y of n is equal to 0 for all values of n which are less than 0. So this notation here is for, this is a standard notation for all values. Okay, so this we have. So this we will solve step by step. So first step is, find system function from LCCDE. So what is our difference equation? So the difference equation is y of n minus 0.7 y of n minus 1 plus 0.1 y of n minus 2, which is equal to 2 times x of n minus x of n minus 2. So what we have here is, so this y of z, if I take z transform, then this will be y of z minus 0.7 z inverse y of z plus 0.1 into z to the power minus 2 into y of z, which is equal to 2 times x of z minus z to the power minus 2 x of z. Okay, so now we'll take out this y of z common. Then we have 1 minus 0.7 z inverse plus 0.1 z to the power minus 2, which is equal to x of z. If I take common, then this will be 2 minus z to the power minus 2. So therefore, y of z upon x of z is equal to 2 minus z to the power minus 2 upon 1 minus 0.7 z inverse plus 0.1 z to the power minus 2. So this thing here is my system function. Okay, so now we have our system function, and the system function is nothing but we define it as define it as h of z. Okay, any questions in finding the system function? Okay, so this was the step 1. Now let's go ahead for step 2. So step 2 is find z transform of x of n, which is x of z. Okay, so we have x of n as 4 to the power n u of n, and this is of the form of, so this is of the form of a to the power n u of n, and multiple times you have seen that this has a z transform as 1 upon 1 minus a z inverse with magnitude of z greater than a. Okay, okay, so this thing we know. So therefore x of z will be equal to 1 upon 1 minus 4z inverse with region of convergence greater than 4. Okay, so we know this thing. Once we know this, the next thing that we need to do is step 2, and that is find y of z and identify poles of y of z.
Step 3, madam.
Yes, so this y of z is x of z into h of z. So x of z is 1 upon 1 minus 4z inverse, and my h of z was 2 minus z to the power minus 2, 2 minus z to the power minus 2 upon 1 minus 0.7 z inverse plus 0.1 z to the power minus 2. Okay, so y of z is 2 minus z to the power minus 2 upon 1 minus 4z inverse, and I can factorize this as 1 minus 0.7, or rather to factorize this 0.7 I can write as 0.5 z inverse minus 0.2 z inverse plus 0.1 z to the power minus 2. So therefore this factorizes something like this. So we have y of z equal to 2 minus z to the power minus 2 upon 1 minus 4z inverse 1 minus 0.5 z inverse and 1 minus 0.2 z inverse. Okay, so now if you observe carefully, we have three poles. So the poles are at these three locations, that is, poles are at z equal to 4, 0.5 and 0.2. So now we know the pole locations, and also one more thing that you can see is there is no pole zero cancellation, so we are safe here. So now what we can do is, the next thing that we need to do is, so this was step 3. So now we have step 4, find y of n. So we know the pole locations and we know the multiplicity of these poles, that is, these are not repeating poles, it is a single pole. So now we can write this as y of n is equal to, so I can write this as a into 4 to the power n plus b into 0.5 to the power n plus c into 0.2 to the power n. And another thing that is given to us is this y of n is equal to 0 for all values of n less than 0. So in order to show, or in order to indicate that this y of n is 0 for all values less than all values of n less than 0, I'll just write a u of n here. Okay, so now what we need to do is we need to find these constants a, b and c. Okay, so we need to find a, b and c. What are these constants that we don't know? So in order to find out this quantity, we need to make use of the difference equation and make use of the conditions or initial conditions or some y of n values that are given to us. So in order to do that, what we will do is, let us first substitute this quantity, this y of n, in the difference equation given to us. So what is our difference equation? So the difference equation that we have is,
Madam, one doubt.
yes,
Can't we write y of z as partial fractions and take inverse Z transform?
we can do that,
Yeah.
but the whole point of this question is the use of the method which was discussed in the class.
Okay. Okay.
Yeah, yeah,
Location of poles.
yes. So in class we had discussed this particular thing, right? Right, right. The solving this for a finite range of time. So
Okay.
we are trying to use this method which was discussed.
Okay.
Okay. So the difference equation that we are having is y of n minus 0.7 y of n minus 1 plus 0.1 times y of n minus 2, which is equal to x of n, or rather, sorry, 2 times x of n minus x of n minus 2. Okay, so now let us substitute the value of y of n. So what is y of n? So this is a4 to the power n plus b into 0.5 to the power n plus c into 0.2 to the power n minus 0.7 into a into 4 to the power n minus 1 plus b into 0.5 to the power n minus 1 plus c into 0.2 to the power n minus 1 plus 0.1 into a into 4 to the power n minus 2 plus b into 0.5 to the power n minus 2 plus c into 0.2 to the power n minus 2, and this thing here is equal to, so this thing here is equal to 2 times x of n is 4 to the power n minus 4 to the power n minus 2. So I am skipping writing u of n because both of these things are valid only for n greater than or equal to, or yeah. So I'll have a u of n here, u of n minus 1 here, u of n minus 2 here, and a u of n here. So this we know what is going to happen. So let's not get into those things. So now what we will do is, this thing, like all of these three terms will be non-zero when I'm having n equal to 2. So in order to do that, what I'll do, in order to survive all of these terms and by some observation, what I'll do is I'll substitute n is equal to 2. So if that is the case, then this first bracket here becomes 16a plus 0.25b plus 0.04c minus 0.7. Then we have 4a plus 0.5b plus 0.2c plus 0.1, and this thing here will be a plus b plus c, which is equal to 2 into 16, that is 32, minus 1, that is 31. Okay, so this thing we have here. Now what we will do is we'll combine the terms corresponding to a, b and c respectively. So what we will do is, let's consider this a. So the terms corresponding to that is 16 minus, this is 0.7 into 4 plus 0.1. Then we have b, and terms corresponding to that is 0.25 minus 0.7 into 0.5 is minus 0.35 plus 0.1, and terms corresponding to c are 0.04 minus 0.7 into 0.2 is 0.14 plus 0.1, which is equal to 31. Now this quantity here is 0.25 minus 0.35 plus 0.1, this becomes 0. In similar way, this quantity is also equal to 0, and what we are left with is this quantity, which comes out to be 13.3. So if you solve it, this is 13.3a, which is equal to 31, and this gives me a value of a as 2.331. So this is the value of a that we are having. You can use calculators to check if it is correct or not. So now we know the value of a, and next what we need to do is we need to find what is the value of b and c. Okay. So let's do that. So we have y of n as a into 4 to the power n plus b into 0.5 to the power n plus c into 0.2 to the power n, and this is for n greater than or equal to 0. So now what we will do is let n equal to 0. So y of 0 will be equal to a plus b plus c, and the value of a is 2.331 plus b plus c. Now this y of n, now we know the difference equation also. So my difference equation was y of n minus 0.7 y of n minus 1 plus 0.1 y of n minus 2, which is equal to 2 times x of n minus x of n minus 2. Now if I substitute n equal to 0, I have y of 0 minus 0.7 y of minus 1 plus 0.1 y of minus 2, which is equal to 2 times x of 0 minus x of minus 2. Now we are given that for n less than 0, y of n is 0. So this quantity is 0, this quantity is 0, and my x of n is 4 to the power n un. So again we have a u of n here, so this quantity is also equal to 0, and x of 0 will be equal to 1. So therefore we have y of 0 as 2 times x of 0, which is equal to. So now this was value of y of 0 which we had, and this is the value of y of 0 which we are getting from difference equation. So therefore 2.331 plus b plus c is equal to 2. So therefore b plus c is equal to minus 0.331. So this is the first equation that we are having. So basically we had two variables b and c which we need to find out. So for finding two variable values we need at least two equations. So we have one equation, we need another equation. So in order to find another equation, what we'll do is we'll consider n equal to 1. So what we'll do is we'll consider now consider n is equal to 1, and this first we will do for the difference equation that we are having. Or yeah, let's do it for difference equation first. So my difference equation was y of n minus 0.7 y of n minus 1 plus 0.1 y of n, which is equal to 2 times x of n minus x of n minus 2. So this will become y of 1 minus 0.7 y of 0 plus 0.1. So this is y of n minus 2, y of minus 1, which is equal to 2 times x of 1 minus x of minus 1. So again this quantity will be equal to 0, this quantity will be equal to 0. The value of y of 0 we had found out here, which was equal to 2, so that we can substitute here. So this quantity is equal to 2, and this y of 1 we don't know. So this y of 1 is equal to 2 times 4 plus 2 into 0.7. So this comes out to be 9.4. Okay, so this is the value of y of n, y of 1 that we are having. Now we know that this y of n is a into 4 to the power n plus b into 0.5 to the power n plus c into 0.2 to the power n. So this y of n, or rather y of 1, will be 4a plus 0.5b plus 0.2c, which is equal to So this comes out, this is equal to 9.4, which we had just found out. And the value of A we had found out earlier. So the value of A is 2.331. So we can substitute that here and take it this side. So what we'll be left with is 0.5B plus 0.2C is equal to 9.4 minus 4 into 2.331. Okay, and this thing here comes out to be 0.076. Okay, so now we are having two equations. First equation is B plus C is equal to minus 0.331, and second equation is 0.5B plus 0.2C, which is equal to 0.076. So this, what we are having is simultaneous equations with two variables. In order to solve this, what I'll do is I'll multiply this by 0.5. So I'll have 0.5p plus 0.5c, which is equal to minus 0.1655, and I'll subtract these two. So I'll have minus 0.3c, which comes out to be 0.2415. Therefore my c is equal to minus 0.805. Now I know the value of c. I'll substitute it in this equation here, that is b plus c. So from that, so this b minus 0.805 is equal to minus 0.331. So this b comes out to be 0.474. Okay, so now what we have is my A is equal to 2.331, B is equal to 0.474, and C is equal to minus 0.805. And we wanted to find out the value of y of n, and my y of n was equal to a to the power n, sorry, a into 4 to the power n plus b into 0.5 to the power n plus c into 0.2 to the power n un. So this comes out to be 2.331 into 4 to the power n plus 0.474 into 0.5 to the power n minus 0.805 into 0.2 to the power n multiplied by u of n. So this is the value of y of n that we wanted to find out, or rather this is the answer that we were looking at. Any questions? So let me just revise what we did. So we wanted to find out y of n, or an approximate equation for y of n for given input for this particular difference equation which is given to us. So in order to do that, what we did is we first found out the system function from the given difference equation, which is my h of z. And after finding that, we went on to find out the z transform of x of n, which is x of z. So this is what we had. After that, what we did, we found out y of z, which is equal to x of z into h of z, and we identified the poles of this y of z. So once we have these poles, we used, or we made use of these poles without doing any other things like partial fractions, just in order to find out an approximate equation. So for that we had y of n, we wrote it as, since we had a single pole at every location, as a 4 to the power n plus b 0.5 to the power n and c into 0.2 to the power n un. This un is coming up because we are given that this system output is 0 for all the values of n less than 0. Okay, so after that what remained was to find out the value of this a, b and c, and this a, b and c we found out by considering the difference equation and this relation that we had found out by substituting three different values of n, and this is what we are getting. At the end we had these two simultaneous equations and we found out the value of a, b and c, and this is the final output that we are having. Any questions in this particular part? Any questions? Okay, if there are no questions, then let me move on to the next question that I have planned to cover. Okay, so in this question what is given to us is a definition of a special type of system which is known as minimum phase system. So what it is said is a system is said to be minimum phase if that system and its inverse both are causal and stable. Okay, so now what we need to do is we need to identify which of the following can be a minimum phase system. Okay, so now let us try to understand what is happening is, so what is given to us is a definition of minimum phase system. And what does it say? It says that, second, yeah, so this says that h of z and a system, let's say h tilde of z, which is given by 1 by h of z. So this is the z transform of inverse of system. So these both are, this one and this are both causal and stable. Okay, now this is given to us. Now just looking at the z transform, how can we say if the system is causal and stable? So in this we'll use the concept of ROC, and what the ROC tells us about the stability and causality. So for stability, what we know is unit circle, that is r equal to 1 should be in region of convergence. This we know. And for causality, z tending to infinity should belong to region of convergence. Okay, so now let us try to understand this with the help of pole zero plot. Or so we have this real part of z here and we have this imaginary part of z here. and let's say this thing here. So this thing here is unit circle. Okay, so this is our unit circle. Okay, so for stability, this unit circle should be in region of convergence. And another thing is we are looking at these LTI systems or rational form of systems. So this region which extends to Z tending to infinity, something like this. So we should have a region of convergence which is like this, that is outwards to the outermost, to the locus or the contour which is given by the outermost pole. Okay, so now suppose I have a pole here. If I have a pole here, its region of convergence will be something single pole. Let's say I have a single pole. Its region of convergence for it to be causal should be like this. Right. So now if that is the case, this unit circle is not included. This unit circle is not included inside in the region of convergence. And therefore this system won't be stable. It is causal, but it's not stable. Okay. Now, in similar way, I have this thing only. Now I want this system to be stable, so my region of convergence will be something like this. Now here my system is stable, it includes region of convergence, but my Z tending to infinity is not included in my region of convergence, and therefore this particular system is not causal. Okay, so now if I have a pole outside the unit circle, that is here, if I have pole outside the unit circle, maybe here, anywhere, a pole which is having magnitude greater than 1, if I have for that particular system, I cannot make that system, or I cannot find a time domain representation for that particular system which is causal and stable simultaneously. So for this particular kind of poles, so for these particular kind of systems where we are having a pole with magnitude with magnitude greater than 1, these kind of systems are not causal, or rather cannot be causal and stable simultaneously. Okay, now suppose I have a pole inside the unit circle, let's say here. Okay, so now for this particular kind of pole that I am having, its contour will be something like this. So there are two possibilities of region of convergence. One is this. So if I have this, then this is neither causal nor stable because my unit circle is not included in ROC, and Z tending to infinity is also not included in ROC. Now suppose I look at the other possibility, which is this. So now here my Z tending to infinity is also included in my region of convergence, and my unit circle is also included in my region of convergence. So when I'm having this kind of pole, or a pole which is inside the unit circle, then in this situation, like for this particular pole, take different color. Yeah, for this pole, so what this pole is having, magnitude less than 1, we can find a system which is causal and stable simultaneously. Okay, so now this we did for a single pole, right? Now, can we extend the same idea for multiple poles? So let's try to do that also. So we did it for a single pole. Now let's try to extend it for multiple poles. So let's say this is my unit circle. This is unit circle with 1 as magnitude. This is my unit circle. And so what we said that if I have a pole inside, then I can find a system which is causal and stable simultaneously. And we said that if I have a pole outside, then we cannot find a system which is stable and causal simultaneously. So let's discard this particular idea and let's focus this. So what I'm having is this quantity here. So let's have a pole here. So when we are having a single pole, we saw that we can find a stable and find a system that is stable and causal simultaneously. Now suppose I add one more pole which is outside. So now the possible region of convergence are this. One is this one. So this is stable but not causal. Another one is this one, which is outside the outermost pole. This is causal but not stable. And the last one is this. Again, this is not causal, but it is not causal, neither stable. So these are the three possibilities. So again, when I'm having this pole outside, one pole outside and one pole inside, can't find causal and stable system. Right. Now this pole I still have this pole, and let me add another pole here like this. So now this is inside my unit circle, and the three possibilities will be one we are having here and another is here. So first possibility is this outside thing. Now if you observe carefully, here my unit circle is included in my region of convergence. Also, the z tending to infinity is also included in my region of convergence, and therefore in this particular situation, when I'm having a pole inside my unit circle, so for this particular situation, I can find a system that is causal and stable simultaneously. So what we can conclude from it, from this discussion is, so a remark that we can make is, if all the poles of h of z are inside the unit circle, then we can find h of n corresponding to this h of z, which is causal and stable. And even if I have one pole which is outside the unit circle, I can't have a causal and a stable system, or rather I can't find a system which is both causal and stable simultaneously. So this is the remark that we are having here. Now what we are given is a definition of minimum phase system. So what it says is this h of z and 1 upon h of z, these both should land to a system which is causal and stable. Okay, so now let us take an example here. Let's say, for example, my h of z is 1 minus 2z inverse upon 1 minus z inverse. Okay, this is my h of z. So here my poles are, or let's do it like this, half and 1 by 4. Yeah. So here my poles, or rather I have a single pole, is z equal to 1 by 4. Okay, so since I have a pole inside, I can find a system that is causal and stable. Now let us look at 1 by h of z, which is equal to 1 minus 1 by 4 z inverse upon 1 minus 1 by 2 z inverse. And here for this my pole is z equal to half. Again it is inside unit circle, so this will also be causal plus stable. Right. So now these two systems are causal and stable, so therefore this thing here is minimum phase. Now you observe carefully, this is my original h of z, and this denominator thing will give me poles for this particular h of z. Now if I invert this particular thing, my zeros will become poles. Zeros of h of z will be poles of 1 upon h of z, and similarly poles of h of z will be zeros of 1 upon h of z. Okay, now if you observe carefully here, this pole of h of z was inside this unit circle, that's why this was causal and stable. And pole of 1 upon h of z, which is actually zeros of h of z, if those are inside the unit circle, then it is known as then this 1 upon h of z is also causal. You can also find h of n, which is causal and stable for 1 upon h of z also. Okay, so what we can conclude is, if both zeros and poles of h of z are inside unit circle, then that system is known as a minimum phase system. So let me write that as a remark. If both zeros and poles of h of z are inside the unit circle, then we can find h of n, which is minimum phase system. Okay, so from definition of minimum phase system, we have landed to a checking condition for finding, or rather checking, whether the given h of z will land us to a minimum phase system or not, and that is we need to check whether both zeros and poles of this transfer function, or rather the system function, are inside the unit circle or not. So now let's get back to the question that we were looking at. So what is given to us? Identify which of the following can be a minimum phase system. So let's start with the first one. So for the first one, we have h of z as 1 plus 10 Z inverse. So if you observe here, we have a pole, or rather we here, if you observe carefully, we have a 0 at Z equal to minus 10, and magnitude of Z is greater than 10. Since we are having a 0 outside unit circle, this thing here, this thing here is not a minimum phase system. Okay, now let us look at the second. So this we saw for this particular question. Now let us look at the second one, that is this one. So we have h of z as minus 2 by 3 z inverse plus 1 minus z inverse by 6 upon 1 minus 1 by 4 z inverse. So this I can write as minus 2 by 3 z inverse multiplied by 1 minus 1 by 4 z inverse plus 1 minus 1 by 6 z inverse divided by 1 minus 1 by 4 z inverse. So this thing here is minus 2 by 3 z inverse plus 1 by 6 z to the power minus 2 plus 1 minus 1 by 6 z inverse upon 1 minus 1 by 4 z inverse. So this thing here is simply 1 minus 5 by 6 z inverse so this h of z that we are having is 1 minus 5 by 6 z inverse plus 1 by 6 z to the power minus 2 upon 1 minus 1 by 4 z inverse, which is equal to 1 minus 1 by 2 z inverse multiplied by 1 minus 1 by 3 z inverse whole divided by 1 minus 1 by 4 z inverse. Now if you observe carefully, zeros are at 1 by 2 and 1 by 3, and pole is at 1 by 4. So in this particular case, since both zeros and poles are inside unit circle, h of z is minimum phase. Okay, now let us do the same thing for third one, that is this one. So what we have is h of z as minus 100 plus 101 upon 1 minus z inverse by 10. So this thing here is minus 100 plus 10 z inverse plus 101 upon 1 minus 1 by 10 z inverse. So this comes out to be 1 plus 10 z inverse upon 1 minus 1 by 10 z inverse. So here we have a pole, we have a 0 at minus 10, and we have a pole at 1 by 10. And since we have this quantity here, this 0 is outside unit circle, and therefore this is not minimum phase. Okay, and similarly, let us do the same thing for the last one, which is this fourth one. So we have this h of z as 1 upon 1 minus 10z inverse plus 21z to the power minus 2. You can factorize this something like this. So I have 1 minus 7z inverse minus 3z inverse plus 21z to the power minus 2. So this I can write as 1 upon 1 minus 7z inverse into 1 minus 3z inverse. So here I have poles at 7 and 3. Both are outside unit circle. Which means that this is also not minimum phase. So what we saw is only this particular option, which is the second one, was minimum phase or can be a minimum phase. Rest all are not minimum phase. We are at the end of this particular question. If you have any queries, please let me know. Is this question clear? Any queries in this part? Is it clear? Okay, if there are no questions, then let me move on to the next question. Just a second. Yeah, so this is the 7th question that I have planned to cover. So it says that which of the following statements is incorrect? Okay, so it is asking us which of the following statements is incorrect, and the first statement that is given to us is all poles lying on the unit circle, the system may be causal. Okay, so for the first part, what is given to us is pole zero plot, which is something like this. So this is my unit circle, which is, let's say, 1. This is 1, and I have poles which are something like this. Let's say I have a pole here, I have a pole here, I have a pole here. So if I'm having poles which are in this form, then the possible cases of region of convergence is this. Sorry. And second possible region of convergence is something like this. And since all poles are at unit circle, there is no pole at z tending to infinity also. So therefore, if I have a condition which is something like this, this yellow region will give me a causal system. And this thing here will not give me a causal system, so it will give me a non-causal system. So the statement that says is if all the poles are lying on unit circle, a system may be causal. So if I work in this particular region of convergence, in this particular region of convergence, which is shaded in yellow, then the system can be, or the system is causal. So this thing is correct. Okay, so this is correct. So now let us look at the second statement. So it says that if ROC includes unit circle, then system must be stable. So yes, this we have seen, we have proved this also in the class. So yeah, if ROC includes unit circle, then the system must be stable. This is also correct. Okay, the third point which is given to us is the highest magnitude pole is half. The system can be causal and stable. So yes, now what it is given is, we are given that the highest magnitude pole is half. The discussion that we did in previous question, in order to understand the stability based on the location of all the poles, so we are having a pole, this is having a magnitude half. So this pole is inside the unit circle, which means that we can have a system which is both causal and stable. So this particular point, this third one, is also correct. Now let us look at the the fourth one. So it says that a causal system can have an ROC which is in the form of an annulus or an annular ring. So what it says is, one pole that I'm having is, let's say, somewhere here, which is like this. And let's say I have another pole which will give me a contour, or yeah, a contour something like this. So let's say this pole is here and this pole is here. So I'm having something like this, and what it says is I'm having a ROC something like this. So if this is the case, we cannot include, or rather the necessary and sufficient condition, that z tending to infinity condition is not satisfied. So z tending to infinity is not included in region of convergence or ROC, and therefore this is incorrect. Therefore we can't have a causal system, or rather a causal system cannot have an ROC as annulus. Okay, which means that this particular option is the answer. That is, we can't have an ROC which is in the shape of annulus or annular ring. Any questions here? Okay, if there are no questions, then let me go ahead with the next question, which is question number 8. So what it says is, given the response, so this is the response, impulse response that is given to us, which is h of n, which is minus 2 delta n plus 10 delta n minus 10 plus alpha to the power n, 10 plus 2n plus 77n square plus 4n cube u of n. Which of the following statements are correct? So we need to look at which of the following statements are correct. So what it say, first term, that's what it says is only the term minus delta n minus 2 impacts the stability. Now you look at this particular term. This particular term has a z transform as minus 2, z to the power minus 2. This spans over entire z plane and has poles at z equal to 0, which means that this term will correspond to a z transform whose region of convergence will include a unit circle. Or rather, we say that this particular thing here and this particular thing here is are constant terms. These are not exponential terms, these are constant terms, and these won't be impacting stability. So therefore this particular thing will not make you lose out your unit circle from ROC. So therefore this term will not impact my stability. The next thing is only the term delta n minus 10 impacts causality. Now this delta n minus 10 is itself located at n equal to 10. It is not giving you an impulse at negative values of n. So therefore, in order to break down the causality, this term won't be a culprit. Right? Okay. Yeah, I made a mistake here. This shouldn't be causal. This should be stable. Or rather, I've missed on one term, causal and stable. Yeah. So if magnitude of alpha is less than 1, then the system is causal and stable. Now if you look at this term here, causality is there. Now this u of n is making it right hand sided, and everything less than for n less than 0 is 0. So now we have this alpha n. So basically what I'm trying to say is this particular system is causal. Now the only thing that we need to take care of is stability. So the stability will be affected by this quantity only, or by this quantity. Okay, it won't get affected by these things. So this will be an exponential decay, and this exponential decay will make the system stable if my magnitude of alpha, that is if this has a magnitude less than 1. If it has a magnitude higher than 1, then this first term itself will diverge, that is 10 into alpha to the power n. It will only diverge, and therefore the system will not be stable. So therefore this particular option is correct. And just now we argued that due to this u of n and these two terms which are there at n equal to 2 and n equal to 10, constant terms, therefore this system is not causal, is a wrong statement. This system is perfectly causal. Any questions? So the answer to this question is option 3. Any questions? Yes, sir.
Madam, in assignment we are getting multiple answer questions and multiple choice questions. Uh, your presentation is not distinguishing that one. Can you say that question is multiple answer or multiple choice question? That means the number of answers are correct or single answer is correct, like that.
Multiple answer question and multiple choice questions both will have multiple answers correct.
No, bullet means single answer only. No, radial point will be having single answer only.
Radial
No.
point will have single answers. If it is a
Uh,
checkbox, then it will
uh,
have multiple answers.
but your presentation is not telling whether it is a checkbox question or bullet question.
Okay, sir. From next time, this like the template that I'm using, I wouldn't be able to do it. I'll mention that it is multiple answer question.
Okay,
Next
thank
from
you.
next time, I'll
Thank you,
mention
thank
it.
you. Thank you.
Yeah. Any other questions? Okay. If there are no questions, then let me move on. Okay. A system has the system function as follows: h of z is equal to z minus 1, z minus 1 by 3, z minus 1 by 2, and z minus 3. The ROC is not known. Which of these can be true for the system? So this is a multiple answer question. Multiple answer. Okay, this has multiple answers in this. Okay, the ROC is not known. Which of the following can be true for the system? So now what we can observe from this particular system is, here I have zeros at 1 and 1 by 3, and I have poles at 1 by 2 and 3. Okay, so let me draw it. So let me also draw a unit circle here, just for reference. So this is unit circle. I have a pole at half here, and I have a pole at here. Okay, so I'll have a circle here which corresponds to half, and a circle which is here, or let me just go out of scale. This, so this is 3, and I have a 0 at 1, and I have a 0 at 1 by 3, which is somewhere here. Okay, so this is my pole 0 plot. Now zeros are anyway not contributing to stability and causality here. So the first possible region of convergence is this one. Now when I'm having this particular region of convergence, this yellow one, this does not include my unit circle, and neither it includes the z tending to infinity term. So for this particular yellow term or yellow region of convergence, the system is neither stable nor causal. So the system is neither causal nor stable. So this last option is correct. So this is the one of the options which is correct. Okay. Now second possible region of convergence is this region, which is here in purple color, which looks something like this. Okay. Yeah. So this is the second possible region of convergence. Now here if you observe, the unit circle is included in this, which means that it is causal, but the z tending to infinity is not included, which means that, sorry, unit circle is included, which means that this is stable, but z tending to infinity is not included, which means that it is not causal. Therefore, this particular purple region will give me a stable system but a non-causal system. So the system is stable but not causal. So this thing is also correct. So this third option is also correct. Okay. Now the third part, or the third region of convergence that I can have, is everything which is outside this thing, which I am shading in green, which is something like this. Okay, and this particular region, if you look carefully, this does not include my unit circle, which means that this system is not stable, but it includes z tending to infinity, which means that it is a causal system. So this system, which is indicated or which will have a region of convergence given by this green shaded region, will be causal but not stable. So the system will be causal but not stable. Now any of these three possible region of convergence won't give me a system that is causal and stable. So this we can also see from the discussion that we had in that minimum phase question. So if you observe here, the poles are at half and 3. So all the poles are not inside my unit circle. This z equal to 3 pole is outside my unit circle, and because of that I can't have a system which is both causal and stable simultaneously. So this options 2, 3 and 4, this 2, 3 and 4 are the correct answers. The first one is not a correct answer. Is it clear? Any questions? Okay, if there are no questions, then let me go on to check to the last question that I have planned to cover today. So this is the 10th question for today. So it says that let h of z be as defined in the previous question. So let me just write down this h of z which I had in the previous question. So it says that h of z is equal to z minus 1 into z minus 1 by 3 upon z minus half into z minus 3. Okay, so now this is h of z that I'm having. Then the question is, which of the following systems in cascade with h of z be both causal and stable? So what it's saying is, I have this h of z, a system here, and I'll have another system which is g of z, and this I'm connecting in a cascade. So this is h of n, this is g of n, and we know from the properties of convolution that this equivalent thing will have impulse response as h of n convolved with g of n, which means that this thing will have the z transform as h of z into g of z. So this cascade system, so this thing is equivalent to a system with system response as h of z into g of z. Okay, so now what is asked is, what system block should I connect in cascade with this h of z such that this equivalent system which I am getting is both causal and stable. Okay, so now if you observe this h of z here, this causality and stability is affected by poles, not zero. So now let us just focus on the poles. So now this particular pole which is at z equal to 2, z equal to 1 by 2 is well inside the unit circle, and this is not my troublesome pole. So the troublesome pole here is z equal to 3. And since this is outside the unit circle, this is making it impossible to construct or to have a system which is both causal and stable simultaneously. Which means that the system which I am connecting in cascade should cancel out this pole. Which means that z equal to 3 should be a 0 of that system. And because of that, I'll be able to cancel out this particular pole. So let me write it down. In h of z, z equal to 3 pole is troublesome. So let me write it, makes it impossible to have a system which is causal and stable. So therefore g of z should cancel z equal to 3 pole of h of z, which means that g of z should have a 0 at z equal to 3. Okay, so for this particular thing, if I look at the options, then this has a pole, this has a 0 at z equal to 2, so this is not our option. It won't cancel out it. This has a pole at z equal to 3, and this also has, sorry, this has a 0 at z equal to 3, and this also has a 0 at z equal to 3. Again, this doesn't have a 0 at z equal to 3, so this option and this option are out of our reach. So what two possibilities are option 2 and 3. So using this particular statement, option 2 and option 3 are possible answers. Okay, so this what these two options are doing, they are cancelling out the z equal to 3, which is troublesome pole, which is here. Another thing that we need to take care of is this g of z itself shouldn't add a troublesome pole. And what are the troublesome poles? The poles which are outside the region of convergence. So the other thing that we need to look at is this g of z should not add a pole with magnitude greater than 1, because if I have this kind of situation, then this will again not give me a causal and stable system simultaneously. So now this condition we haven't checked yet. So if we check this condition and look at the options again, so these two are our possible options or possible answers, this one and this one. Now let us check at the poles of these two systems. So first pole that we are having is at z equal, this second option is having a pole at z equal to 2, and this is not getting cancelled with any of the zeros of this h of z, and therefore this thing is a troublesome pole here, and z minus 1 by 3 is okay. We are fine with this particular pole. So this again is not our option. Now let us look at the third possible answer. We have this 0 here, and the poles that I'm having is at z equal to 4 by 5 and z equal to 1 by 3, which means that both of the poles of this particular function are inside the unit circle. Also, it is cancelling out the troublesome pole of my h of z, and therefore this particular option is my answer. So option 3 survives. So this option 3 is our answer. Any questions? So this is the final answer that I have. Any questions? Any questions in any part of this tutorial? This was the last question that I have planned to cover. Okay, that's all I had planned to cover today. If you have any questions, then please let me know. Otherwise, you're free to leave the meeting. Thank you for attending today's session.